Okay, so it means now the vectors, you can write this vector space H as nothing but span of uh, cos of omega t and sine of omega t. Okay, now so H is a subspace of V, and hence is a vector space. Okay, let's do another example, and in this example let's assume that H and K are uh, some subspaces of vector space V, and these are subspaces, right? Now the sum of we have to show that if H plus K is a subspace of V, right? So if H and K are in some vector space V, what we have to show that H plus K is a subspace of V, right? To do that, right, we assume that given H and K, so H is a subspace, K is a subspace. So the first condition is that zero vector should be in H plus K. So if H is a subspace, it will have a zero vector. If K is a subspace, it will have a zero vector. So it means 0 plus 0 will effectively be 0. It means the sum of H plus K has also a zero vector, right? Now if I say now let's take two vectors in H plus K. So there is a subspace H plus K. If we assume that, right, and there are two vectors, W1 is equals to U1 plus V1, another vector, let's say W2 is equals to U2 plus V2, and these are the vectors in H plus K, right? So these W1s and W2, right? U1 and U2 are the vectors in H, and V1 and V2 are the vector in K. Okay, then we can say that W1 plus W2 is nothing but equal to U1 plus V1 plus U2 plus V2, right? So that comes out to be U1 plus U2 plus V1 plus V2, right? So because the vector addition to V is commutative and associative, right? So it means U1 plus U2 is in H, and this one is in K, right? So these are the vectors in H plus K space, right? So it means the second property is also satisfied, that indicates that the vectors in H, when you sum H plus two subspaces H plus K, when you sum them up, the vectors in H and vectors in K also adds up, right? Now similarly, for the third one, we can say that if W1 is a vector in H plus K, that means C times is U1 plus V1, which is C times U1 plus C times V1, right? U1 is a vector in H, right? Means C times U1 is also in H and is also in K, right? So this is the vector in H plus K, right? So this third condition is also satisfied, indicating that if H is a subspace of V and K is a subspace of V, H plus K is also a subspace of V. Okay, now in the second part we have to show that that H is a subspace of H plus K, and K is a subspace of H plus K. Right, now certainly you can see it from here as well, right, that H is a subspace of H plus K, because every vector u in H, right, for example here u1 u2, right, may be written as, you can write it as say u1 plus say u1 plus 0, right, where the 0 vector comes from K, right. Now since H contains a 0 vector of H plus K, right, and H is closed under vector addition multiplication by scalars, because H is a subspace of V, H is also a subspace of similarly the same argument applies for K as well, right, indicating that H is a subspace of H plus K and K is a subspace of H plus K. So in this example what we have shown here is that to summarize, that sum of two subspaces will generate another subspace, right, and if second part is that if there are two subspaces, right, if a subspace is addition of two subspaces, individual subspace are actually the subspace of that sum. So in this case we can see here H plus K is a subspace, so it means H is a subspace of H plus K and K is a subspace of H plus K. Okay. Now let's conclude this discussion on subspaces. In the next lecture we'll talk about in detail about the column space and the null space. Okay, thank you. Assalamu alaikum. Welcome to the lecture of linear algebra. Today we'll talk about vector spaces. Okay. So so before we start with the details of vector spaces, there are a few things that we should define before we really understand a vector space. So vector space is a non-empty set V of objects called vectors, right, on which are defined two operations called addition and multiplication by scalars. By scalars or real numbers, and they are always real numbers. Okay. Now generally a vector space is must follow 10 axioms. So if you say there are vectors u and u, v and w in a vector space, first of all is that sum of u plus v is in V, right? So if there are vectors u, v and w in vector space V, right, So the addition of two vectors u plus v is in v, and also the second one is v plus u is equals to u plus v, and similarly third one is u plus v plus w and u plus v plus w. Okay. Now the fourth property is that zero vector 0 is in V such that 0 plus u any vector should be u, right? Okay. Now and for each u in V there is a vector minus u in V such that u plus minus u equals to 0. Okay. Now the sixth one is if you multiply a scalar number to a vector. So if you multiply a scalar c by u, then c times u is also in V. Similarly, seventh one is c into u plus v is equals to cu plus cv, and eighth is that c plus d times u, and c and d are scalar here, cd plus cu plus du, right? And the ninth axiom is c times du is actually cd times u, and the 10th one is one unit vector u. If you multiply unit vector with another vector, this should also be in u. Okay. Actually, technically, if we talk about V, right? So V is actually a real vector space. V is a real vector space. Okay. And generally all of the theory that we are dealing in this course is actually relates to real numbers and real vector space, although similar observations are equally valid for a complex vector space. Okay. In which rather than using scalar numbers you will be using complex numbers. Okay. So the space Rn for n greater than 1 are generally the prime example of vector spaces, are example of vector spaces. Okay. So for another example, let say S be the space of all doubly or say infinite sequence of numbers. So you can write that as something y of k is starting from somewhere, y minus 2, y minus 1, y0, y1 and y2. So so if let's say zk is another element of S, then from the axiom that we just studied, then yk plus zk is the sequence, actually yk plus zk, right? So what we can think here is your yk plus zk is nothing but equals to, from that is y of minus 2 plus z of minus 2, y of minus 1 plus z of minus 1, y of 0 plus z of 0, and so on and so forth, right? Similarly, if you multiply any scalar number to y of k, then if you say c times y of k, then you say that the sequence becomes c times y minus 2, and there's of course so on and so forth, right? Using the axioms in that we just written over in the last page. Now, now this element of S, like this sequence of numbers, generally arise in a lot of engineering applications. For example, if you are sampling the signal in speech signals, or there are communication signals that being transferred from one place to another, and of course in control as well. So we'll call S as, normally this S is written as the space of discrete time signals. So for example, there is a signal, let's say there is a pulse wave here, so we may want to sample the signal, because that's what you do in signal processing and communication system. You sample the signal and then apply some kind of operations on that signal. So actually that all these values that you are getting actually form a sample space, right? So the one like we've written over here, so y, so if I say this as 0 1, or let's say this is -1 -2, right? So this could be y of t here, so this could be k here, and this could be y of k here, right? So this value is y of -2, this could be y of -1, and so on and so forth, right? Now so specifically, so this is an example of a vector space. So one other example is, let's say for n greater than 0, right, the set of polynomials. So it is also form the set n, also form the sample space, because you can write p of t as a naught plus a1t plus a2 t square plus up to a n t n, right? So these also form a vector space, right? So if there is another function, let's say q of t, which is b naught plus b1t plus b2t b2t squared, so b n t n, right? The sum of this one as p of t plus q of t is nothing but equals to a naught plus b naught plus a1 plus b1 t plus similarly, right? So so the axioms of the vector space are followed by this kind of function Bn. Okay. Yeah. Now in many problems we are actually interested in not the complete vector space, right? We are interested in an appropriate subset of vectors in the vector space, right? So for example, in this case, like for example here, we may not be interested in the all set of values from -infinity to infinity. We are only interested in the values taken by the signal. Okay. Similarly, in other cases as well, right? For example, if we are controlling let's say a motor, or designing communication system, we are interested in like for designing a motor, we may be interested in the amount of control voltage that we can apply, which may be between 0 to 20 volts, right? So this is the range of values. So sometimes you are interested in the set of appropriate set of numbers or vectors for some larger vector space. So these are called subspaces. Okay, so a vector space consists of an appropriate subset of vectors from some larger vector space. Okay, now so in this case, when we are talking about some specific set of vectors, we don't need to actually say to check. We don't need to check all the 10 exomes for this subspace formation. We often need to check only these 3 exomes that I'm writing over here, that the 0 vector of V is in H, right, where H is the subspace, okay, and V is the bigger space, or here we are saying that as vector space. So if V is a vector space and H is a subspace, the 0 vector of V is in H. So we can say that if H is a subspace of V, right, the 0 vector of V is in actually that subspace. H is actually closed under addition, and such that if there are vectors in H, that is in H that has 2 vectors U and V, that U plus V is also in H, right? So and the third one is it is also closed under multiplication, such that if there is a vector U, then you can say that C times U is also in H, and C is a scalar here, right? So these are the scalar value. Okay, so one of the very simple examples that you can derive from any vector space V is a 0 subspace, right? So 0 subspace is the set containing all the 0 vectors, right? So all containing of only the 0 vector in a vector space V. So what you take here is, from a vector space V, we just actually take the 0 vectors, right? So so is called a subspace of V, and you can normally write this as 0, right? This is called the 0 subspace. Okay, so another example of a subspace is so the one we discussed earlier. Let P be the set of polynomials, set of all polynomials with real coefficients, right? With only real coefficients. Right. With then we can say P is a subspace of all real valued functions defined on R, right? So remember, this was a naught plus a1t plus a2t square and so on, right? Okay. Now similarly for any n also, we can say that for each n greater than 0, Pn is the subspace of P, right? So okay, now now we say P be the set of all, so P is a vector space here. So P be the set of all polynomials with real coefficients, then P is a subspace of all real value functions defined on R. For that, Pn is actually the subspace of this P here, right? Now similarly, also that we need to check all these three axioms for P of n. If it really follows that three axioms, so we have seen here it actually does say, for example, here P of t plus Q of t, here we can say that C times P of t is also becomes A naught C plus A1 C plus A2 C t squared and up to plus C times A n T n. Okay. Okay. Now few things that one should be careful of is that the vector space R square actually is not a subspace of R cube, R3, sorry, not cube, R3. So you cannot say that for example, let's say it is A B C, you cannot say that this is a vector in R cube, right? Now if there's a vector AB, right, which is in R square, so you cannot say that AB is a vector, is a subspace vector of R3, because the thing here is you have to really understand this. This has to be that this subspace H is in V, right? But this R square, this vector is not in R cube, right? So you have to be really careful in understanding that R cube, this R2, any vector in R2 is not actually a subspace of R3. Okay, it is only the set of possible vectors in R3 can be, then that be define the subspace H, right? Not these kind of vectors. Okay, and also that what you have to really understand that if a plane in R cube, or let's say a line in R square, or a line in R2 that does not passes through the region, define the subspace, right? So for subspace definition, right, remember that that zero vector of V is in H, right? So any set of plane, any set of vectors that define a plane, or any set of vectors that actually define a line in R2 or R3 that does not pass through the region actually cannot form a subspace. Now similarly, we can define a subspace by the set of vectors, right? And as you remember, as we have seen in the last chapters as well, that one of the simplest way to define a subspace is by a span of vectors which is V1 up to Vp. Okay. Now the term linear combination, so what we happens here is span is nothing but you know that C1 plus C2 V2 up to C and CP Vp, right? So all possible linear set of combinations of these vectors can actually define a subspace, right? with the conditions that all these vectors follow the three exomes, right? All these the span defined it by these vectors. um, all the vectors that are in that span actually should satisfy the three exomes. Now generally so let's do an example. Let H be the set of all vectors of the form, let's say a minus 3b, b minus a comma b, where a and b are arbitrary vectors. So then what we have to do is show that H is a subspace of R4, right? So we can write this as nothing but equals to a minus 3b, b minus a minus a and b, right? So you can write this in terms like this: a 1 minus 1 1 and 0, similarly b as minus 3 1 0 and 1, right? So you got here a as v1 plus b times v2. Now if you compare this one with this one, right, H actually is nothing but the span of v1 and v2, because a and b are arbitrary scalars, not vectors here, sorry. So a and b are arbitrary scalars. So and it is just very similar to this definition of the span. So v1 and v2 vector, the span of v1 and v2 vectors define H. Now we have to show that H is really a subspace of R4. So to show that, right, we have to prove that three exomes are satisfied by this H, right? So first of all, we can see that the zero vectors should be in H. Zero vector should be in H, right? So now to do that, right, so we can show that if a is 0 and b is 0, right, so it means this includes the zero vector. Second one is the addition of in this vector a1 and if say v1 plus v2 should also be in H, right? And also we have to do is multiply these vectors by another by a scalar quantity, right? That it should be also in H, right? So so what we can write this as, in the first scenario we can say that for the first part, which is the zero vector v is in H, so zero vector v is in H, right? So in that case we have 0. If I put a0 b1 plus b as 0, I'll get an answer as 0, right? So it means zero vector is in H, right? In the second case we have to show that it is close under addition. So if it is close under addition, it means if I have vectors let's say x as defined as a1 v1 value plus b1 v2 okay, b2 v2 value, and then let's say we define this vector x, then try vector y as a2 not a2 then, okay, let's make it okay, let's make it t1 v1 plus t2 v2, right? So if I add x plus y, then I should get here is a1 v1 plus b2 v2 plus t1 v1 plus t2 v2, right? So that comes out a1 plus t1 into v1, right? And this comes out to be v2 plus t2 into v2, right? Now it means since a and b are arbitrary scalars and then taking out the real values, so it means a1 t1 will be also a real value, so indicating that the sum will also be in H, right? So this a and b, very similar to that. Now third one is if I multiply any vector by c, so if I multiply c to x, right, I get here is c times, so I get here c times a1 v1 plus c times b2 v2. So we can see here these are nothing but the scalar multiples, and the vector cx is also in H because c times a1 is a scalar value, this is a scalar value, and we know that this H is defined by all the possible linear combination of the linear values of a and b. So we can do another example. Say for what values of H will y be in the subspace of R cube spanned by vectors v1, let's say 1 minus 1 minus 2, v2 is equals to 5 minus 4 minus 7, v3 is equals to minus 3 1 and 0, and y is equals to minus 4 3 and H. So the question here is if these three vectors define the vector space, so what value of H will guarantee that this y will also be in H, right? So we know that from our previous understandings that you can solve it for by making an augmented matrix, and so once we have that augmented matrix, we can convert it into the echelon form, reduce echelon form to calculate the values of the values that can correspond to H. Okay, now so what we can do here is we can make an augmented matrix here: 1 minus 1 minus 2 5 minus 4 minus 7 minus 3 1 and 0. So you can make here minus 4 3 and H, right? Now once we have that augmented matrix, we can carry out the row operations on that. So it means I can add the first row to the second row and multiply the first row with 2 and add it here. So if I do that, that becomes here as 1 5 minus 3 minus 4, so added here is 0, right? This becomes 1, this becomes minus 2, this becomes minus 1, and multiplied by 2 here, so 2 0 here, 10 3 here, and becomes minus 6 and becomes minus 8 plus H, right? Now similarly I can do another step here and remove that, and that is 1 5 3 minus 4, and if I do that, it becomes 0 1 minus 2 minus 1. Multiply this with 3 and subtract it from here, so you got 0 here, so 3 this becomes 0 here, so 3 minus 2 will be 6 minus 6, and subtracting here will become 0 here, and 3 minus 3 here, and minus 8 plus H minus 3, so that will be minus 8 plus H minus 3, right? So it means for that vector to be in y to be in this vector space v1 v2 and v3, you have minus 8 plus H minus 3 should be equals to 0. Okay, and okay, so it means that should be, so if you multiply by 3 here, so what you have here is multiplied by 3 inspected from here, so that will be 1. This becomes 0, so minus 6 and minus 6, and you got here is minus 6, so minus 6 and minus your minus 6 will actually be 0. Okay. Now, so what we did was we subtracted the second row, multiplied the second row by 3, and subtracted from the third row, which is comes out to be 3 minus 3 0, and minus 6 and minus 6 will be 0 again here, and you multiplied by 3 here, so minus 3 and minus, so that becomes plus, sorry, here. So h comes out to be 5. Okay, so you can also do some examples of subspaces. Let's say one of the exercise problems that I'll be doing here is let H be the set of points and on the unit circle in the xy plane, right? And that is, you say H is equals to xy such that x square plus y square is less than 1. Okay, find a specific example. Two vectors or a vector and a scalar to show that H is not a subspace of R2, right? So so what it's saying here is this is x and this is y here, right? So we can make this circle. So we're saying H is a vector space that is defined by the points on the circle and inside that circle. Now, since we know that this is the circle, and equation of the circle we know that is x squared, if it's a unit circle becomes, and it's at the origin, the equation of circle is x squared plus y squared equals to 1, right? But since we are talking about all the points inside the unit circle as well, so x squared plus y squared is less than 1, so it's saying that this is the vector space. So saying that it's a vector space, but you have to show that it is not a vector space, and we have to give some examples to illustrate that it's not a sample space. So so what we need to say that here is we have to remember the 3 axioms of a subspace. First one is that the 0 vector is in subspace, right? So 0 vector is in subspace. So in this case, if x is 0 and y is 0, right, and which in this case it is, right, the first axiom is we say x is equal to 0 and y is equal to 0 is satisfied, right? Now let's look at the second axiom, and in which we say that if I add 2 vectors, right, in this subspace, I should get a vector in that subspace, right? So if I, for example, add a vector here which is 0.5 and 0.5, and another one as 0.5 and 0.5, let's say 0.5, right? So I've taken let's say 0.5 and 0.6. okay, so let's take a vector u, this is a vector v, right? So these are u and v is in h, right? So both these vectors are in h, right? But if I take u plus v, which will be somewhere here, right, and v will be somewhere on that side, right? Now if I add them up, what will happen here is they will actually go out of H, right? So it means U plus V is not in H. They are in, actually individually they are in H, right? But as a sum, their sum is not in H, right? So it means second exam is not satisfied. Now if you look at the third example, similarly take U. So if I take C, if I multiplied C by any scalar, right? So C can be 4. So 0.5 times 0.5, and this comes out to be 2 and 2, right? So we know that 2 and 2 vector is not in that space, because 2 and 2 would be somewhere at that point, right? So it means this set of points H defined by H under this condition cannot form a subspace. Okay, let's take another example. If it's a mass spring system, and we know that in a mass spring system, displacement of y of the mass from the resting position, right? So if there is a spring here, my drawing is not that good anyways, but and there's mass attached here with a spring. Okay, so the displacement y from the resting position here, which is, if I let go of this mass, displacement y of the mass from its resting position actually can be written as y of t is equals to c1 cos of omega t plus c2 into cos sine of omega t. Now omega is actually, we know, it's a constant that depends on the parameters of the spring and the mass, this mass m attached to it. Now so we have to show that the set of all functions defined by this equation, is with omega fixed and C1 and C2 arbitrary, is a vector space, right? Now remember this, if you're so it means you have to show that this is a vector space. Okay, now in order to show that a vector space, this is quite easy to show that, right? So it means I can think of now as this as cos of omega t, and this as sine of omega t. So in this case I can write y of t as you can say as c1 0 as cos of omega t plus 0 c2 sine of omega t, right? Now the vectors that becomes oh sorry, should have written other way around. That is y of t is c1 cos of omega t and 0 plus c2 times 0 sine of omega